Hello, hello. We are working through integration. Today we're talking about definite integral properties and accumulation functions. And I like this stuff. It's pretty cool. So I am ready to dive in. Given that some function y equals f of x is a continuous function on AB, shown below, suppose we define some function whose area under the curve is between point A and some other point x. We can denote the area under a curve as a definite integral. And we'll define this as a new function, capital F of x, where x is somewhere between A and B. And this is what that looks like. So we have capital F of x equals, and you could think about this as saying the area under the curve between A and x under the curve of little f of t. The fundamental theorem of calculus, part 1. If f is continuous between A and B, then the integral function is continuous on AB and differentiable on AB, and this is the money right here. F prime of x, capital F prime of x equals little f of x. Or you could write it this way. The derivative of big F of x equals the derivative of the integral of f of t. In English, the fundamental theorem of calculus relates differentiation and integration, showing that these two operations are essentially inverses of one another. The graph of f is shown below. Evaluate the following if g of x is the area under the curve between -6 and x of our function f of t. So f of t is a derivative graph, okay? And if we're looking for g of something, we're looking for the area under the curve between -6 and whatever this x value is. So first thing we have to do is put some areas in here, which I'll do for you. So between -6 and -4, there's a trapezoid there with an area of 4. And then that little sliver is 2.75. And then the next trapezoid is 5.25. And then up until 4, we have a trapezoid with area of 12. And then 4 to 7, we have a trapezoid with an area of 9. Okay, with all of those areas there, now let's find g of -3. So we're starting at -6, and we want to find g of -3. So what's the area under the curve? It's 4 plus 2.75, which is 6.75. Now we want g of 0. So again, we're starting at -6, and we're going all the way to 0. So 4 plus 2.75 plus 5.25 is 12. If we want g of 4, we just got to keep going to 4. So we add 12 to that, and we get 24. And then if we want g of 7, we continue all the way, adding all the areas together, and we get 33. Well, these have all become points. We've got -3, 6.75 is a point on g of x. So is 0, 12. So is 4, 24, and 7, 33. So we just have to plot those on a graph, and there we have g of x. Isn't that cool? When area is negative, at times we will integrate functions that do go below the x-axis. So please keep in mind, area below the x-axis counts as negative area. The total area between A and B for some curve is actually a net area. We'll use this one as an example. So g of x equals the area under the curve between 0 and x of this function shown at the right, f of t. We're going to complete a table of values for g of x, kind of like we did before. First thing we need to do is sum areas between our function and the x-axis. So we've got a rectangle of 2, trapezoid of 3, triangle of 2, another triangle of 2, a rectangle of 2, and a triangle of 1. Now let's go back to our table. If we have an input of 0, that means we want g of 0. So we want the area under the curve between 0 and 0. Well, we haven't gone anywhere, so there's no area under the curve. If we have an x of 1, then we want the area under the curve between 0 and 1. And you can look at the graph, and that's that rectangle of 2. So you can see where we're going here. With an x value of 2, we want g of 2. So the area between 0 and 2. So that'll be 2 plus 3. That's 5. And continuing on, g of 3 would be 7. But at 3, our function dips below the x-axis. So now these areas that are coming up, 2, 2, and 1, those are going to count negative. All right, so g of 6. Right, so we want the area under the curve between 0 and 6. We want to go all the way over here. So at 3, we were at 7. When we keep going to 6, we have to subtract 4. And then if we keep going all the way to 7, we have to subtract 1 more. So we have an area under the curve of 2. Now we have these xy points that we can graph. 0, 0, 1, 2, 2, 5, 3, 7, 6, 3. Notice it went down, 7, 2. And you can connect the dots for your g of x graph. So this is the parent graph, and this is the derivative graph. On what intervals is g of x increasing? Now you can look at either graph. If you look at the derivative graph, g of x is increasing wherever the derivative graph is above 0. So that's between 0 and 3. If you look at the parent graph, that holds true. Look at it's increasing between 0 and 3. Where does g of x have a maximum value? At 3, the maximum is 7. Let's try another one. Shown below is the graph of the derivative of f for some function f. Assume f of negative 3 equals negative 8. Mathematically, this is what we're looking at. We have a starting point of negative 8. That's a y value at x equals negative 3. From there, we're looking at area under the curve. Anything to the right of our starting point is area that we're adding. Anything to the left of our starting point is area that we are subtracting. All right, so f of 2, we're looking for the area under the curve between negative 3 and 2. So we've got negative 8 plus 10 plus 26 is 28. F of 6, okay, we're going to keep going all the way to 6. Add up all those areas. We've got negative 8, that's our starting point, plus 10 plus 26, and then minus 8 plus 14. That's 34. F of negative 5. Okay, now since we're starting at negative 3, we want to go backwards to negative 5, so we're subtracting the area that we come across. So that would be negative 8 minus 18, which is negative 26. Leibniz, he was a famous mathematician, introduced the notation for the definite integral. The Greek letters of summation became the Roman letters in the limit. So this notation is read the definite integral from a to b of f of x with respect to x. Let's break this down. Each of the component parts have names. This, like S thing, that's the integral. B is the upper limit. A is the lower limit. F of x is an integrand. D of x, or whatever's in that spot, shows the variable of integration. And then the whole thing is called the definite integral. The definite integral can be used to determine the net area or displacement bounded by the x-axis, the function f of x, and the vertical lines x equals a and x equals b. We're going to practice some more with this graph. It says the graph of f of x consists entirely of line segments and a semicircle on the interval from negative 8 to 13. We have all kinds of geometric shapes here. So let's start by just reviewing some of the area formulas that you might need if I weren't here to just give you the areas on there. So pi r squared, that's the area of a circle. 1/2 base times height is the area of a triangle. And 1/2 times the height times the bases added together, that's a trapezoid. So I'm going to mark off some important area segments here. And then we'll go 4. We've got that triangle on the left. And then this semicircle is 9 pi over 2. And then we have a trapezoid of 12, another trapezoid of 8, and then another trapezoid, 15 over 2, and then our final trapezoid of 6. Okay, so part A says find the area under the curve between 0 and 7. Between 0 and 7. 12 plus 8 is 20. B, we're going all the way to 13. 0 all the way to 13. So 12 and 8, those are added, and then 7.5 and 6 are subtracted. So 20 minus 13.5 is 6.5. C, we want the area under the curve from negative 6 to 0. So negative 6 to 0, negative 4.5 pi. The area under the curve from 3 to 3, we haven't gone anywhere, so that's 0. What about the area under the curve from 7 to 0? So if we're starting at 7, then anything to the left is negative. So that would be a negative 20. What about from 10 to 4? So we're starting at 10 and going backwards 4, so we're subtracting it. Or we can actually kind of rewrite that and say negative 4 to 10. So that would be negative 8 minus 7.5. So negative 1/2. All right, negative 8 to 13. Oh, that's the whole thing. Negative 8, woo, all the way to 13. So everything above the x-axis is positive. Everything below the x-axis is negative. That gives us 10.5 minus 4.5 pi. And then h, oh my, what's f prime of negative 6? It wants the derivative at negative 6. the slope of this graph at -6 is, well, see, it's different coming from the left than it is coming from the right. That's a cusp, so our derivative actually does not exist there. Well, what's f double prime of 6? So right here, f prime of 6 is going to be the slope at this point. So that's -2. And then the derivative of -2 is 0. J is asking for the average rate of change over 0, 5. Average rate of change, that is slope f of 5 minus f of 0 over 5 minus 0. F of 5 is 4. F of 0 is 0. So we get 4 minus 0 over 5, which is 4/5. Okay, true or false? The area under the curve between 0 and 2, so we're going 0 to 2 there, plus the area under the curve from 2 to 4. Is that the same thing as the area under the curve from 0 to 4? Yes, it is. And L, over which values of x is f of x not differentiable? Okay, so anytime we've got a cusp or a point on this graph, then we're going to have a non-differentiable point. So at -6, we already saw that, and then at 0, and then at 2, oh my, and then at 5, 7, 8, 11. Wow. It's a very pointy looking graph, isn't it? Properties of definite integrals. The definition of the definite integral of f from a to b specifies that a is less than b. That's like understood. However, it is convenient to extend the definition to look at cases where perhaps a equals b, or what if a is greater than b? Number one, if f is defined at x equals a, then the area under the curve from a to a is 0. We haven't gone anywhere. If f is integrable, I always struggle with that word. If f is integrable on AB, then the area under the curve from B to A is negative of the area under the curve from A to B. And we saw that earlier. 3, if you can integrate f on 3 closed intervals determined by A, B, and C, then A to B equals A to C plus C to B. If we can integrate both f and g on an AB interval and k is a constant, here's some other things we know. If there's a constant inside the integral, we can pull it out to the front. If you're finding the area under the curve just of a constant line, then it's the constant times the ending point minus the starting point. And then finally, if you've got two functions being added together, you can break those integrals and add them separately. So we'll practice that. Use the properties of integrals to evaluate each of the following, given that a to b of f of x dx is 8, a to b of g of x dx is -3, and a to b of h of x dx is 5/2. So with that in mind, what is b to a of g of x? Well, that's going to be negative a to b, so that'll be 3. B. What's the area under the curve from a to b of twice the function? Well, that too we can bring out to the front. And we know that a to b of f of x is 8, so this equals 16. A to b of 5, so that's going to be 5 times b minus a. We don't know what b or a are right now, so we'll just leave that there. D, I've got two functions being added together, so I can split the integral. And then this guy, a to b 5, well, we just figured that out there. And then g of x is negative 3. So 5 times b minus a minus 3. E is asking about the difference of two functions, and we can just split that integral. F of x is 8, h of x is 5/2. So that one's about 5.5. And then F is interesting. We're going A to 4 and 4 to B. And since 4 is the connection point there, we can just go straight A to B. So that's going to be 5/2 or 2.5. Well, this looks complicated, doesn't it? If the area under the curve from -1 to 5 of 3 times f of x plus 4 equals 34, what's the area under the curve from 1 to 5 of just f of x? This is actually just algebra, because we can split this integral, okay, into two integrals, and then this constant we can move forward. So watch this. 3 times the integral from 1 to 5 f of x dx plus the integral from 1 to 5 4x dx equals 34. This guy we can figure out. That's 4 times 5 minus 1. Okay? And then the other one, we'll just leave that for a second. 4 times 5 minus 1 is 16. Subtract 16 from both sides. And see, I'm just trying to get this guy by himself. And we're almost there. We just divide both sides by 3, and there we go. The area under the curve of f of x dx is 6. We will be using a ton of definite integrals later on in the course, so glad you were here to learn it. See you next time.